In this lecture, we are going to learn about the field of brain cognitive engineering, specifically in the topic of decision-making, learning, and brain engineering. What we set as the goal is to understand the mechanisms for evaluation and decision-making. In doing so, we use various methods to formalize behavioral and neural mechanisms, and in turn, aim to reverse engineer human cognitive and affective processes. As you may know, this field of study is highly interdisciplinary and closely linked with other classically defined areas such as economics, psychology, psychiatry, and neuroscience. Due to the large overlaps in the key interests and questions between the fields, the research we conduct as a team is often defined and referred to by several different names, including neuroeconomics, decision neuroscience, and computational psychiatry. Main research interests we have can be formalized in a simple choice problem. How can we compare apples and oranges? If the two options we are deciding between are 1 versus 2 apples, it will be a very easy question because it simply becomes a numerical comparison. However, because apples and oranges are fruits that are entirely different in their color and taste, among other features, comparing apples and oranges is a decision problem quite more difficult than we think. And from a different perspective, the fact that we can easily make choices in these types of decision problems indicates that our brain is capable of processing a lot of complex information together and somehow makes use of it. When a decision maker makes a choice, the only information we, or even the decision maker herself, can observe is the choice itself. In the field of decision neuroscience, we make one simple assumption about decision processes to understand their underlying mechanisms. An observed choice reveals the preference of the decision maker, and one step farther, we can assume that the person placed a higher value on the choice over the alternatives. In short, if a person makes up a certain type of choice, we can think that there must be a good reason for the choice. Using this assumption is very useful in understanding complex decision processes. If we collect a series of choices in large enough number, we can rearrange the decision maker's choices and extract the person's subjective valuation. A vast amount of studies were done taking this approach and show that such subjective valuation reflects human choice very well. A following question is then, where in the brain is involved in this process? In 2009, Chip and colleagues conducted a study to answer this question and suggested that a brain region called the ventromedial prefrontal cortex represents subjective values of choice options. Because their results were consistent regardless of the type of items that were being considered, it was suggested that there is a common currency in the brain that assists human decision makers in the decision processes. You can also think of the cases where choice options do not guarantee a certain level of rewards. An easy example would be buying a lottery ticket. Everyone knows that there only is a slight chance of winning the lottery, but choosing between buying a ticket versus not, and saving that money sometimes is very difficult. One step further, when one has to make choices between options they yet never experienced, learning about these options through repetition is crucial to making a better choice in the future. The processes of how humans learn about the values of the unknown options are formulated as and investigated in a probabilistic reward learning problem. Reinforcement learning, a most influential theory of learning, suggests that we learn from the errors between expectation and experience, and that we become to minimize this prediction error as we progress in learning. Previously, data from non-human primates showed that dopamine, a neurotransmitter, reflects reward prediction error. Particularly after learning, dopaminergic neurons fired more when the primates viewed the cues associated with anticipated rewards, but do not respond more at the actual delivery of the rewards. Furthermore, when the rewards were unexpectedly omitted, dopaminergic neurons went silent and fired less. This set of data supports that the brain not only tracks the delivery of the rewards per se, but focuses on the errors experienced through the learning process. Functional neuroimaging studies also showed converging evidence supporting the use of the reinforcement learning mechanism in humans. Specifically, meta-analysis show that many neuroimaging studies reported the involvement of striatal regions spanning putamen, nucleus accumbens, and caudate in tracking reward prediction error. According to these data, as the reinforcement learning framework formulates, error signals are represented in the striatal region, and updated value signals are represented in a network of brain regions involved in value-based decision-making. Given that humans are a social being, a lot of daily decisions are made among social others, for others, and with others. When we make choices or learn under such a social context, it is known that we tend to behave a bit differently depending on the specific context information, such as who is present at the place and how these social others are engaged in decision processes. In one example study we conducted, participants were asked to make a series of risky choices, but before making their own choice, they were provided with the choice information of two other anonymous players. Compared to participants' preferences that they would have shown when making choices alone, they tended to follow these social others' choices. That is, when others both chose safer options, the participants showed even more safer choices, and when others' choices were risky options, they also chose risky options more often. By using computational modeling in conjunction with functional neuroimaging, we show that making choices under a social context alters individual subjective valuation, which was represented in the ventromedial prefrontal cortex. Being able to use the information we obtain from social context can be a huge benefit from the learning perspective. If one has to learn solely based on her or his own experience, it may take a very long time or even impossible to go through all possible cases. However, we humans can also learn by observing others. Previous studies show that in a probabilistic reward learning task, individuals were able to take advantage of observing others' experiences and use that information to learn better and faster. What was interesting is that even in the case when individuals only got to observe their choices, without knowing whether the choices were good or bad, participants tended to follow others' choices. In a recent study, Carpentier and colleagues show that such a following behavior people show under social context could be a product of more than just one strategy. When observing others' choices, individuals may make inferences about others' motivation underlying the observed choice, as if thinking on the shoes of social others. Alternatively, making inferences may not work as one hoped, such that emulated choices of social others may turn out to be constantly wrong. In this case, individuals may choose to simply imitate others' choices. It turns out that our brain arbitrates between these strategies so that we can use this additional social information appropriately given this specific circumstance. As I showed today, there are various contexts and different information processes that are involved in decision-making and learning. Formalizing these behavioral and neural processes is not only useful in expanding our understanding of the human brain, but also beneficial in developing artificial intelligence that simulates how humans think and behave. Computational modeling, tailored experimental designs, and neural image analysis can be powerful tools in pursuing this line of research. I briefly showed one line of research in brain cognitive engineering, focusing on understanding human decision-making and learning processes. I believe that understanding the mechanisms of the human brain can be viewed as a reverse engineering problem, which can benefit from well-designed experimental tasks and computational modeling inspired by various neighboring fields of study. Thank you for watching.